Good morning, friends. Last we discussed the 9th question already asked in Neet exam, right? Now the next is depends on the total internal reflection. A point source of a light is placed in the water below 4 meters from the surface of the water. In a medium having the effective index is 5 by 3. Effective index of the water is given, and this is placed on the water surface such that it blocks the light coming out from the water completely. So the minimum diameter of this is, whatever the diameter of the disk required to block the light coming out from the source, already the source is inside the water having the effective index is 5 by 3. Now to explain this, we do the diagram. First thing here, the effective index of water is given 5 by 3. We have to find out the diameter of a disk. D we have to find out. Our figure becomes like this way. There is the container that is filled with the water up to this. A point source is placed in a water at 4 meter depth. Point source is at here. Where is the point source? Just we place the disk on the surface of a water like this way. Depth of source is given h is given the 4 meter. Now, the ray coming from the source incident on the edge. So that is the right angle triangle OAB. AB is the radius of a disk. This angle is critical angle. This angle is critical angle C. Clear? Okay. Now, for total internal reflection and also we derive the equation sin C is equal to 1 upon n. Right or not? Therefore, using this equation from sin C is equal to 1 upon n, and from figure sin C. For this right angle triangle OAB, sin C is equal to opposite upon hypotenuse, right? So is equal to R upon hypotenuse is R square plus H square raised to half. Comparing these two equations, 1 upon n is equal to R upon R square plus H square raised to half. Simplify this equation and substitute the value. We obtain the R is equal to 3 meter. R is equal to 3 meter. Therefore, diameter of a disk is D is equal to 6 centimeter. Right? Okay. Again, very easy numerical. So we know that when this angle or the angle of incidence is equal to the critical angle, at that time this ray of the light is not coming out from the water, that is the reflected in the same medium. That means the total internal reflection takes place. For that purpose, this angle of incidence that must be C. That is C, so this angle is also C. Suppose we assume that here the disk block the light coming from the source. Therefore, the angle of incidence is C. Therefore, sin C is equal to 1 upon n. N is the effective index of a water. And also, for this right angle triangle OAB, sin C is equal to opposite AB upon OB. That means the hypotenuse of this right angle triangle. Now comparing these two equations, so 1 upon n is equal to R upon R square plus H square is to half. Now take the in this side, therefore n is equal to r square plus h square is to half, making the square on both sides, and as we simplify, we obtain the r is equal to 3 meter. That is the radius of a disc, therefore diameter of a disc must be 6 centimeter. So that is our answer. Clear this? So on the base of total internal reflection. Now the next numerical is a lens is placed in between of source and wall. Right? In such a way that the area of image on a wall for two different positions are A1 and A2. Then what should be the area of the source? Now listen, one wall is given. One source is placed on this wall. Here we place the convex lens. The image of this source, the area of the image on a wall for two different positions are A1 and A2. The image is obtained by the convex lens on the wall. There is also another wall. For two different positions, there is the A1 and there is the A2 of a lens. There is the one position, there is two position. The area obtained on the wall are A1 and A2. A1 and A2. There is A1, there is A2 on the wall. Then what should be the area of the source? We have to find out the area of the source. Now here magnification is depends on here the two different positions of a lens, therefore two different positions are A1 and A2. That means here the combination of the two lenses takes place. Therefore the resultant magnification is equal to under root of M1 M2. Therefore area A is equal to under root of A1 A2. That is the answer. Directly said, no any proof of this. Right? Again, here at this position of a lens, here what is the area of the image obtained on the wall? That is the A1. If the distance is between the screen and lens is decreases, so what's happened? Area is increased. Area of the image is increases. Therefore, the magnification is increased. Therefore, the resultant magnification of the combination of two different positions of a lens is M is equal to under root of M1, M2. Now, therefore, the area of a source is equal to under root of A1, A2. Now, next numerical is light passes through a glass slab of refractive index and thickness T. If the C is the speed of the light in free space, then the time taken to emerge out of a glass slab will be. So already this numerical we discussed. In a glass plate of 4 mm thickness, the time taken by the sunlight to pass through this glass of thickness 4 mm. At that time, which equation we obtain? Nt upon C. Here we are using these two equations. Refractive index of a medium is C by E. Therefore, V is equal to C by N. And also, we know that the velocity is equal to distance upon time. Distance upon time. Compare these two equations. Therefore, time taken is equal to N into distance upon speed of a light. Therefore, N, here the distance is equal to thickness, so Nt upon C. Nt upon C. Clear the same? Okay. Again, the light passes through a glass slab of thickness, refractive index N and thickness T. If the C is speed of light in a free space, the time taken to emerge out of a glass slab will be. Now we know that n is equal to c by v. That is the relative effective index. Therefore, the velocity is equal to c by n. And we know that the velocity is equal to distance upon time. Therefore, time is equal to effective index into distance upon c. Now, distance is given as the thickness of a glass slab. Therefore, nt upon c. Now, next numerical. An object on a wall by help of a convex lens. An image of object is obtained of same side of an object on the opposite parallel wall. If the lens is at distance d from the second wall, then the focal length of a lens is. Now listen here. There is the one wall. Source is placed on the wall. The image of this source is obtained by the lens, convex lens, on the opposite and also the parallel wall. The lens is at distance d from the second one. There is the lens. Image provided also the same size for the second one. So then the focal length of a lens is. Okay, now listen here. The same image is obtained. That means the object distance and image distance are same. Here the distance between the lens and other wall. That means the position of an image. In short, that is the image distance is given. That is the d. Now here v is equal to d. But same image is obtained. So, object distance is equal to image distance is equal to d. From equation of lens, because we require the focal length of a lens, therefore, equation of lens is 1 upon f is equal to 1 upon u minus 1 upon, 1 upon v minus 1 upon. But image distance is always negative. Therefore, 1 upon f is equal to 1 upon d plus 1 upon d. That means the 2 by d. Therefore, focal length of a lens is d by 2. Is d by. Now listen. First understand the question what is given. An object is on a wall. By help of a convex lens, an image of object is obtained of same size of an object on the opposite wall. Here the object is placed on a one wall. The image of this object is obtained with help of a convex lens. The image obtained on the opposite and parallel wall is same inside of an object. If the distance between the second wall and lens is d. So what should be the focal length of a lens? Here, the distance between the lens and other wall on which the image is formed is given. That means the image distance is given. Therefore, v is equal to d. And also, the image obtained is also in same side of an object. Therefore, there is possible if and only both distance are same. That means the distance of lens from the first wall and second wall must be same. It means the magnitude of object distance and image distance are also equal to d. Now, using the equation of lens 1 upon f is equal to 1 upon v minus 1 upon u. But we know that the object distance is always negative. Therefore, u is equal to minus v. Therefore, this minus minus plus. Therefore, 1 upon f is equal to 1 upon d plus 1 upon d. Therefore, 2 upon d. Therefore, f is equal to d by 2. That is the focal length of a convex lens. Clear it? Okay. Okay, now next numerical is, here the bioconvex lens is given, is cut in such a way that it's equal to half r x o x dash and y o y dash axis. That means this type of the convex lens is given. As if first divided this convex lens in this part, this axis. So first part and second part, right? Now then we divided this convex lens vertically axis, this part and this part, right? If the focal length of original lens is f, and f dash is the focal length of in case 1 and f double dash is the focal length in case 2, then which of the following is true? Right? Now first section, given lens is divided in two parts this way, x o x dash, there is the o, there is the x, there is the x dash. So as a result, this lens is act like this way. One lens and second lens is this. Clear? Okay. Now, here the R1 and R2, radius of curvature of these two spherically curved surface does not change. Here, R1 and R2 does not change. So the focal length of both, so the focal length of both parts will be same, equal to f dash is equal to f. From equation 1 upon f is equal to n minus 1 upon R1 minus 1 upon R2. There is the inflection by a spherically curved surface. The focal length 1 upon f is equal to n minus 1 into bracket 1 upon R1 minus 1 upon R2. As we cut the lens on the axis x o x dash, so upper part and lower part both has the curvature surfaces are same. Therefore, the radius of curvature of both curved surfaces does not change. Here, the n also not change. Therefore, the frequency, focal length of both lens are same and is equal to the focal length of original lens. Right? Okay. Now in section 2, we cut the lens in this manner. The lens is given like this way. We cut the lens like this. Y, O, Y dash. As a result, we obtain the two plano convex lens like this manner. 1 and 2. So there is the combination of two lenses of same focal length. Is the combination of two lenses of same focal length. Therefore, 1 upon f double dash, 1 upon f double dash is equal to 1 upon f plus 1 upon f, that means the 2 upon f. Therefore, f double dash is equal to 2f. F double dash is equal to 2f. Clear this thing? Okay. So 2 times there is the 1 upon f plus 1 upon f. That means the 1 upon f plus 1 upon f, 2 upon f. Therefore, f dash is equal to 2. Therefore, our answer is whatever the rank, there is the B is rank, f dash is equal to f and f double dash is equal to 2f. Clear this thing? Okay. Now, next is, now listen here. As we cut the lens in either horizontal axis or the vertical axis. The original focal length of original lens is f. As we cut from the horizontal axis, so it divides into the two parts. Here the radius of curvature does not change. Therefore, from equation 1 upon f is equal to n minus 1 into bracket 1 upon r1 minus 1 upon r2. So focal length of both parts is same as the focal length of original lens. Now, as we divide this lens according to the vertical axis, therefore, so resultant part becomes like this way. So here the both part is very close to each other. Therefore, there is act as a combination of two plano convex lens. Here the focal length of both is same, that is the f. Therefore, 1 upon f double dash is equal to 1 upon f plus 1 upon f. Therefore, 2 upon f. Clear this? Okay. Now, next is angular resolution of a telescope is of order of length for 10 centimeter objective diameter and 5000 angstrom wavelength of light. Now listen here, the wavelength is given lambda is equal to 5000 angstrom. We convert into meter. So 5000 into 10 is 2 minus 10 meter. Diameter of object is given, there is the 10 centimeter. Convert into meter, therefore there is the 0.1 meter. Or the 10 into 10 is 2 minus 2 meter. Now angular resolution of a telescope is 1.22 lambda upon capital B. Substitute all this value. So 1.22 lambda. Lambda is 5000 into 10 is 2 minus 10 upon 0.1, or the 10 into 10 is 2 minus 2. Thus we obtain the angular resolution is 10 is 2 minus 6 radian. 10 is 2 minus 6 radian. Again, the angular resolution of a telescope is given is order of length for 10 centimeter objective diameter and 5000 angstrom wavelength of light. So directly we have to use the equation of angular resolution 1.22 lambda upon d. D is the diameter of an objective. Here the wavelength given, diameter given. So as we substitute, we can obtain 10 is 2 minus 6 radian. If here the multiply is present, now here the answer is only given with the what is the multiplier of. We need to find out the answer in only of order 10 is 2 minus 6 minus 2 minus 4 2 like this. So here the numerical value may be present, but ignore it, only 10 is 2 minus 6 radian. Okay. Now next, a combination is formed by keeping a convex lens in contact with a convex lens. If the both have the same focal length of 20 centimeters, so here the f1 is equal to f2 is equal to 25 centimeters, then power of combination is. Now resultant focal length 1 upon f is equal to 1 upon f1 plus 1 upon f2. Right? Okay. Here the both lengths are convex lengths. Therefore, here 1 upon f1 minus 1 upon f2, there is our power. Therefore, 1 upon 25 minus 1 upon 25. So there is the 0. Therefore, power P is equal to 1 upon f is equal to 0 power. Is the 0 power. So there is the power of the combination of two convex lengths are placed in contact. Directly apply the equation of the resultant focal length. Resultant focal length is in reciprocal form, that gives the power. T is equal to 1 upon F is equal to 0. After that, the next question is that frequency and wavelength of light in transparent material are 2 raised to 14 Hz and 5000 angstrom. Frequency is given 2 into 10 raised to 14 Hz. And wavelength lambda is 5000 angstrom. Therefore, 5000 into 10 is to minus 10 meter. 10 is to minus 10 meter. So how we can solve then? What is the effective index? First, find out the speed of a wave in given material, light in given material. V is equal to F lambda. Substitute the value. F 2 into 10 is to 14. Lambda 5 into 10 is to minus 7. Right? Therefore, we obtain the V is equal to 10 is to 8 meter per second. Now, refractive index of a material C upon V. C upon V. Therefore, C is given 3 into 10 is to 8 upon 10 is to 8. That is cancelled. Therefore, 3. 3 is the effective index of a given material. Again, very easy question. Frequency and wavelength of a light in material, transparent material is given. Frequency is 2 into 10 is to 14 Hz and wavelength is 5000 angstrom. Now, frequency is 2 into 10 is to 14, wavelength is 5000 angstrom. That means the 5000 into 10 is to minus 10. It means the 5 into 10 is to minus 7 meter. We require the value of effective index of a given transparent material. For that purpose here, first we have to find out the speed of a light in given material. We know that the speed of a light in given material V is equal to F lambda. F and lambda are given, therefore V is equal to 10 is to 8 meter per second. Now, the effective index of a given material N is equal to C by V. C is the velocity of a light in phase space. 3 into 10 is to 8 upon whatever the value of V we obtain, 10 is to 8. So 3 is the effective index of a material. Clear? Okay. Now listen, a boy focuses the sunlight on a paper by using a bioconvex lens of focal length 10 centimeter. So focal length of an object is given the 10 centimeter is equal to 0.1 meter. Such that the paper can burn. Diameter of a sun is 1.39 into 10 is to 9. Diameter of a sun D 1.39 into 10 is to 9 meter. And distance of the sun from the earth is 1.5. Suppose the distance we take the U. U is equal to 1.5 into 10 is to 11 meter. Find the size of an image on paper. Now what is the situation? Now the sun is like this manner. One boy focus the sunlight on a paper. That is the paper. Now listen here. We have the experience as we focus the sunlight on a paper. So that is the distance of the image is equal to focal length of a lens. V is equal to F. Therefore F is equal to our V. Image distance. Now the distance between the sun and lens is our object distance U. Diameter of the sun, that gives the height of an object or the diameter of object. Therefore we know that V upon U mod of V upon U is equal to image height upon object height. We require this image height d dash upon d. D dash upon d. Therefore, d dash is equal to v upon u into d. V upon u into d. V is given 0.1, u is given this, and diameter of the sun is also given. So we can find out the diameter of a is 9.2 into 10 is 2 minus 4 meter. Again, the sunlight is focused by a boy with help of a convex lens on a paper. So we know that when we focus the sunlight at that time, the distance between the lens and paper must be equal to the focal length of a convex lens. So that is the image distance, V is equal to L. And what is the distance of the sun from the lens? That is the object distance. Because the rays are coming from the sun is the source, right? Okay. Now the diameter of the sun, that means the area of or the side of the object is given. We have to find out the size of an image formed on a paper. For that purpose, a useful equation, mod of V upon U is equal to image height upon object height. That means the d dash upon d. Therefore, image height d dash is equal to V upon U into d. Substitute the value, all values are given. So we obtain the height of an image 9.2 into 10 is 2 minus 4 meter. Option A. Clear this?